Okay, so earlier this week, you guys were working with Hooke's law, which tells us about the forces that are exerted by springs. And so that equation that you guys were working with looked like this. We had this negative kx, where k was a new thing for us. That was a spring constant. And x was a familiar thing, displacement, but it sort of meant a different thing for us when we were talking about springs than it has before. So I'm going to come over to this simulation to just remind us what displacement looks like and get us into our work for this week, or for this end of the week. So we were working with intro for our Monday, Tuesday, Wednesday work. Now we're going to come over to this energy slot for today. And just before we start talking about energy, displacement for us right now means how far we move this spring, either compressing or stretching the spring from its equilibrium position. And speaking of equilibrium position, I'm going to go ahead and click that box over here for now so that this little dotted green line reminds us where that equilibrium position is. So if my displacement is 0 like it is right now, then we can see this spring just sort of sits at its resting place. That's how long that spring would stretch if we weren't touching it at all. So Hooke's law again tells us the force exerted by the spring wherever we compress it or stretch it. We have to exert some force to push, and the spring pushes us back, and that's what Hooke's law gives us. But today, since we, of course, clicked on this energy box, we're going to be talking about energy stored when we compress a spring. You could imagine that anytime you compress a spring, like in your pen, or certainly bigger springs like what you have in the suspension of a car or on a bike, they store energy. And so if we compress the spring and then we let it go, it would sort of bounce back, and it could actually move things. It could launch things into the air. It can do all these different things because it stores energy in there. And the new equation that we have, so we're not looking at forces anymore necessarily, but we're looking at energy. And that new equation is, and I'm going to say EPE, and we've talked about that briefly before, but that's for elastic potential energy. So EPE is equal to 1/2 k x squared. And so the variables we have here are now familiar. That k is still our spring constant. The x is still that displacement. And the interesting thing here is that we can draw a parallel, and I'll just write this above, between this and our kinetic energy equation, which it's been a little while since we've talked about kinetic energy, but that kinetic energy equation was 1/2 mv squared. For elastic potential energy now, we have that it's 1/2 kx squared. We won't go into sort of the derivation of this equation. It would require a little bit of calculus for us, so we're not going to go into that. That's not something I expect you guys to know, but we really need to know how to be able to use this equation. And one way that you're going to be able to use it is that I might ask, and on this Thursday work, I ask a lot, what is the elastic potential energy stored in a spring with some spring constant pushed to this displacement? And those can be straight plugins of this equation. So let's say, I'm going to erase some things just to clear up some space. Let's say we were asked to find EPE when k is equal to, let's say, 200 newtons per meter, and x, or our displacement, is, let's say, positive 0.4 meters. And so one way we could solve this is just by plugging into our equation. So our elastic potential energy equal to 1/2 times k, so that's our 200, times 0.4 meters squared. And it looks to me, and you guys watching the video should check because I'm not sure on my calculator, but I think that looks like it's going to be 16 joules. Remember that joules are our unit for energy there. So if I weren't sure though, and if we're uncomfortable using this equation for now, you can use our simulation as well. As long as our spring constant falls somewhere between 100 and 400, and our displacement falls between -1 and +1 meters, we can actually just use our simulation. So I'm going to come over here on the left side and do that. So our spring constant is supposed to be 200, so I'll drag this little blue marker here, and then I will drag our displacement to being +4, positive 0.4 meters. And I'm going to use these little arrows to sort of fine-tune that displacement a little bit. And I don't see anything yet, because I haven't clicked a couple important things. So when we come over to the simulation, it's important that we click our applied force, displacement, and very importantly, the values one. So that's where it actually tells us in this little bar graph up here for this potential energy thing. It'll show us that we have 16 joules of potential energy, which that's a relief. That's what we got by doing this calculation as well. So those two things should always agree, and you can solve any of these problems if they fall in the range of these spring constants and in the range of these displacements. You can use either that equation or this simulation. The only other kinds of questions that you'll see on this Thursday work is other applications of this elastic potential energy equation where you're solving for something other than potential energy. So I could also ask you, what is the spring constant given this potential energy and given this displacement? Or I could ask you, what's the required displacement if we have a spring with this spring constant and we want to store this much potential energy? I'm going to show a quick example now of how we would solve one of those types of problems. I won't show both here because it's the process is the exact same, just some of the algebra would look a little bit different. So let's say that we have a spring that has a spring constant of 100 newtons per meter, and we would like to store, let's say, 4,000 joules of energy. So it's going to need a pretty big displacement. And our question is, how much do we need to compress or stretch this spring to make that energy happen, right? To store this much energy in our spring. So I'm just going to plug in the values that we know. We know that our elastic potential is 4,000. The next part of that equation is 1/2 times now our K value, and then we don't know X yet. So I'm going to multiply our 1/2 times our 100. That gets us 50. And then we still just have our 4,000 on the other side. So since we're looking for X, I'm going to get rid of whatever is next to that X and divide both sides of this equation by 50. It looks like that is going to give us 800 being equal to X squared. And now I do not know what the square root of 800 is. So let's pull out a calculator. 800, take the square root, and it looks like X would be equal to 28.3, I'll round to, meters. So we would have to compress or stretch this spring out a lot. It would have to be a pretty gigantic spring for us to store this much energy in it. Most springs probably could not be stretched 28 meters. That's a pretty ridiculous answer. But that's how you would solve any problem like that, where if you know an energy and a spring constant, we could solve for that displacement. The way that you would solve for spring constants is actually a little easier. You don't have this taking a square root step. So it actually, that's the same thing as this without that last step of taking a square root.